Hello friends, welcome to my channel. So in this video we will be predicting the house price using the multiple linear regression. So it's a very interesting project to be added in your resume, and I have the complete source code also in the description box. So please go through this video multiple times to get the confidence on this project, and this will definitely get an attention from different employers once you add it to your resume. So let's get started. So let's go through the problem statement. So here actually a real estate company wants to predict the price of the properties in a specific region. So they have a data set that contains different attributes. So area, bedrooms, parking space, whether it's furnished or non-furnished. So there are lots of attributes. So what this project is about, the company wants to understand that which all different attributes affect the price of the house, and also they just don't want to know the attributes. We want to quantify them as well. So for an example, which attribute is affecting how much, so that quantification we have to do, and also we need to know the show the accuracy of the model, how these variables are predicting the price. So this is an overall summary of the problem statement. So we have divided this project into multiple steps. So when we're building the model, there are multiple steps that will follow. So let's start with the reading and understanding. So first we will read the project and understand it, and then we will visualize the data, and then we will prepare the data for modeling. So basically we'll split the data into train and test, and then we'll rescale the data to bring all the data into the same scale. And then we will train the model. So in training the model, we will understand the different coefficient, and then we will go with the residual analysis, and then we will evaluate the model after doing the prediction. So let's start with the first step quickly. So we will start with importing our friendly libraries, numpys and pandas. So first of all, I'm using a Google Colab for this project. So it's a very important and very helpful tool. So to write the Python code on the browser, and it contains all the pre-built libraries. So what I did is I have already added the housing CSV file in this Colab. So I'll also add this in the description box so that you can download it, and then when you are writing this, when you're working on this project, so you can also import it. So by the way, a disclaimer is, when going through this video, please write the code along with going through the video so that you get a good understanding, and also you get a good hold of writing the code. So please go and write each of these commands one by one in your own Colab notebook as well. So let's start with importing the libraries, so NumPy and pandas, and then I'm using the pandas read CSV method for reading the file, so housing.csv. So let's go. So now, as usual, like we will be just looking at some data. So the data frame. So now it's a housing data frame. So after that, it converts that into the data frame and storing that in the housing variable. So I'm reading. So data frame has a method called head. So that gives you the top 5 rows and all the columns. So by the way, I already have a video on the data frame. So please go through that. It will help you to understand this video much better. So now we can look at the data. So it has a pricing column, area, and then a bedroom. So we can see there are some categorical values, yes, no, and then different attributes are there, and then furnishing status. So it gives a pretty good understanding of how the data looks like. So let's look at the shape. So shape gives you how many rows and columns it has. So it says like the columns is 545 rows it's having, and then the 13 columns. So rows on the column. And we can look at the complete data frame using the info method. So now the info method gives you the complete picture. So it's saying 545 entries, and it has 13 columns, and there is no non-null value. So that's good actually. It saves a lot of data cleansing, and this is different data types available. So sometimes the data you get, the data doesn't is not basically ready to use. You need to do a lot of cleansing, like it contains a lot of null values. It contains so then you need to clean up those null values or fill those null value with some mean or medium values. So I have actually another video on exploratory data analysis. So that's a data science project, interesting data science project. So go through that. That will help you to understand how to clean up the data, or how to basically go through and fill up the data with some where the data is empty, how you can fill up those data. So go through that video. It gives you pretty good understanding on it. So now there is another method called describe. So this helps you to get some summary or numerical summary of the data. So if we run this, so you can now see like different uh, the mean of the different columns, the most all the numerical columns, and what is the 25 percentile. So it gives you the range how the data is being spread also. So the max value and then minimum value, and then if you will see like the area it's spread across like this, and then 50%. So that's mean the how the median and the mean looks like and how close they are. So it gives you some good numerical and summary of the whole data. So let's spend some time and then visualize the data. So this helps to understand the data, because first of all, we have to look at whether there is a linear relationship between the predictors and also the outcome variable. So basically the dependent and the independent variable, the price and other attributes. And also we need to understand whether there is a multicollinearity exists. So that we will, that I'll explain later also. So we will visualize the data using the matplot and seaborn libraries. So I have imported the matplots and seaborn libraries already. So now let's use the seaborn pair plot method. So what it helps is actually you can visualize different columns on one screen. So it will be taking all the numerical columns and then show that all on one screen. So okay, so now that looks much better. So so all the diagonal actually shows the column. So how the data is distributed for a specific column. So it's showing the price and the area, and then if I'll go this column wise, so it's showing like how the price is related to area and then bedroom. So because this is the price, so this is the x-axis and the y-axis are different columns. So price to price histogram. So well, if you look carefully for the area, you can see there is a linear relationship. So as the price is increasing and the area is also increasing, so if we can see there is a linear relationship between the area and the price column. So that uh, that signifies that yes, we can go ahead and build a linear model. And if we move further, so we can see that the bedrooms actually, so as the number of bedrooms are increasing, the price is also increasing uh, until 4, and we see like some changes in 5 and 6, so it's not that drastically increasing. And similarly, there are the bedrooms. So as these are actually numerical, but actually these are categorical values. So we have a different actually methods for visualizing. So we can go ahead and build a box plot that helps to visualize the categorical variable as well. So how we can do is I have already went through and figured out which all different categorical variables we have. So what we will do is, instead of visualizing one by one, we can visualize all in one screen. So what we have, we can use the matplot subplot method. So what it says is matplot subplot, and then 2 is the number of rows we want, and the 3 is the number of columns. And this is like the first graph. So it says 2 rows, 3 columns, and first graph, 2 rows, 3 columns, and second box plot, 2 rows, 3 columns, third box plot. So you can define what all box plot you want in that specific box of the subplot, and then the figure and figure size, you can control the whole figure size using the figure size in the figure method. So in the box plot, you have to define like x-axis, what will be your x-axis, and this is the y-axis as price, and this is the data that we want to pull for showing on the box plot. So let me run this. Okay, pretty good. It's pretty impressive. So if you will look here as let's start with at the main road. So if you will see that if it is at the main road, then the price are going, it's more compared to if it is not on the main road. So that means there is a relationship between the main road and the price. And similarly, if we see the guest room, if there is a guest room, the prices are high compared to non-guest room. Basement, not seeing much relationship. And similarly, air conditioning, there is a good relationship, and also with the furnished, semi-furnished. So that way we can conclude that the categorical variable is also uh, is dependent on the price, and actually the price changes based on the values changing in this variable. So also what we can do is we can compare multiple variables also. So what we can do is we can use like three variables at a time in one box plot. So I'm giving the x-axis as furnishing status, and then I'm giving the price, and we have hue that I'm giving air conditioner. So if I just run this one, so now what it is showing is for furnished. So this is furnished and semi-furnished, and then here it's showing whether it's an air conditioner or not. So this is basically showing two variables dependent on price. So so basically, if this is uh, this has an air conditioner and it is a furnished, so the price is it's pretty high compared to and semi-furnished when so when this is semi-furnished and it's air conditioner compared to. So what I'm saying, what I'm telling here is there is actually a relationship between these variables also. If these variables are also affecting the price together, so that says like this there is a multi-collinearity exists. So that's what if the variables are dependent on each other and affecting the outcome variable or the predictor, then we say there is a multicollinearity exists, and we need to get rid of that multicollinearity also. So there are different methods also. So before we move forward, let's do some data preparation for this. So if we look carefully, let's go above, and then uh, so if you look at it, there are a couple of columns that have either yes or no. And so what happens is actually that linear regression model needs all the values to be numerical, not a string. So we need to convert these yes or no to ones and zeros. So one as a yes and no as a zero, and then there is one more column called furnishing status. We'll work on this later, but let's actually take care of the one where there isn't yes and no. So I have added all those columns in this variable. So all these are added as a list. So now what I'm doing is I'm applying. So there is a method in the data frame series that I can use apply. And then what I'm doing here is I'm using the lambda function. So I'm mapping this when if it is yes, mark it as 1, or it is no, mark it as 0, and then it will take the values from each of these variable one by one and apply the lambda function. So after running this, so let's run this. So now let's see the data frame again. Okay, wonderful. Now all these now are changed to 0, 1, and now the one left is the furnishing status. So pandas have a method called the get dummy. So this get dummies actually help you to convert this categorical into a numerical, and they call it as a dummy variable. So once that is converted, so what it does is actually it take these values and then change them into 1 0. So it makes the combination. So let me show you first how this happens. So I'll use the get dummies, and you just provide what column you want to convert into the dummy values. So furnishing status. So if I'll run this, so let's see how this, and by the way, I'm storing this value in a new data frame called status. So let's check how it looks like. So what's happening here is it's converted actually now if it is furnished. So if you look at it, the first value is furnished. So it is changing the furnished to 100, and again it's furnished 100, and if it is semi-furnished 010. So wherever the value is furnished, it's making in when rest as 0. So that way it's converted all the different status to categorical by changing it to 1 wherever the value is that furnished in the furnishing status. So it created these 3 dummy variables. But if you will look carefully, so we actually can drop one of the column here because things are redundant here. So if you will see 00 can corresponds to furnished, and then 01 can correspond to unfurnished. And then if we have 10, then it can be semi-furnished. So in that case, we don't actually require the first column. When it is 00, we can say this is furnished. When it is 10, we can say semi-furnished. And if it is 01, then unfurnished. So that way we can reduce the number of columns also. So in order to do that, there is another attribute in the get dummies called drop first. So if you make the drop first at true, it will remove the first column. So let's run that, and after that it has removed the first column. So now what we have to do is we have to actually combine this with the original housing data frame. So we will use the pandas concat method. So we give both the data frame as housing and status, and we will be giving access equals to 1. The reason for access is because we want to concat them column wise. So column wise we give access 1. If you want to do row wise, then access equals to 0. So let's concat them, and then let's see the head of the data frame. Okay, looks pretty nice now. So now this is semi-furnished and furnished. So now we need to drop this furnishing status column. So we will use the data frame drop method for this, and again housing drop and the column name, and then access 1 because we want to drop column wise, and then in place true, basically it make the changes right away. So in the data frame, so now let's look at head. Okay, now our data frame looks pretty clean now. So it now ready for moving to the next step for splitting that into training and test sets. So for splitting the data into training and test set, we will be using the scikit-learn model selection train test method. So what we have to do here is we can use this method directly. So we can either do it by ourselves also, but this help actually to do it pretty clean way. So what we have to do is just define the test train split and the method, and then the data frame that we want to, and then we can give the train size. So 0.7 means 70% of the data will be in the train size, and the test size 0.3. You can just give 1 also. The method will take care of it. So if you just give the test size 0.3, so method will assume by default that the rest is 0.7, and random state I am giving 100. So that means whenever I run this again and again, it will produce the same data set. And then what it does is it will store the train set in the TF data frame, and the training set and the test set in the test data frame. So basically what we are doing here is we are splitting the data set into training and test. So training will be used for learning the patterns in the data set by the model, and then we will once the model is completed and learn the pattern, then we'll use that model to evaluate the model on the test set, because that will be a new data for the model. They haven't the model didn't saw that data, so that way we can evaluate the accuracy of the model better. So that's why we are splitting the data into training and test sets. So let's run this now. Okay, so now our test data is in the DF test data frame, and train data is in the DF train data frame. So now one important thing here is actually we need to rescale it. So rescaling is very, very important step actually, because if we don't have a comparable scales, then some of the coefficient as obtained by fitting the regression model might be very large or very small compared to other coefficients. So basically this will affect the model evaluation. So it is always advised to standardize or normalize the data so that coefficient obtains are all on the same scale. And the two important ways to rescaling is min-max scaling and the standardization. So min-max scaling is actually we subtract the values from the minimum value and divide that by max minus minimum. And in the standardization, we subtract by the mean and divide that by the standard deviation. But this time we will be using in this project the min max scaling. So we can import that from the scikit-learn, so min max scaler class. So let's import it. And then we will create the instance of min max scaler and store that in the scalar variable. So now what we have to do is like all the numerical variables. So where the values are actually not in between. So let's look at actually those first. So if I say df train dot head. Okay, so now like some of the columns already have the values from 0 to 1. So for those we don't need actually to run the rescale it because it's already there. So we need to rescale it where the values are not between 0 and 1. So by the way, the min-max scaler, there are two techniques that I talked about. The min-max scaling, so that makes the value between 0 and 1, and standardization actually standardize the value and centralized it uh, along the mean. So the mean will become 0 as a standardization, and the value will be spread across the mean. So basically, when the values are 0 or 1, we don't need to rescale, and rest we have to rescale. So I have added all these variables in this num variable and added that into the list. And then after that, we have actually, there are a couple of methods for min-max scaler. So first is fit, and then other is transform, and the fit and transform. So what fit does is actually it looks at it analyzes the whole data and make it ready for the transform. So basically, it will go and look for what is the minimum value, what is the maximum value, and make the data ready. And the transform will run on that data, that the formula, and then change it the new value. So that way both are split. So why this is, I'll explain you later when we'll evaluate the model. And there is another method, fit and transform, that can do both the things together. So we will run the fit and transform here. So the scalar method, and then fit and transform on df train only on these columns, and then update those columns. So let's run this now. Okay, now let's look at the head. Okay, so now you can see all those values are scaled between 0 and 1. So now let's look at the numerical summary also. Okay, so now you can see like all the max values are 1, and also the minimum values are 0, and it is spread between 75, 50 percentile. So now you can easily see now the values are between the range of 0 and 1. Okay, so now let's check the correlation coefficient. So basically what we are trying to do here is we need to see uh, how these variables are related to the predictor variable. Basically what we have to analyze here is how the price is impacted when we change other variables. So Seaborn has a pretty nice method for this, like a heat map. So we can use a heat map of the Seaborn to look at the correlation coefficient between them. So as I explained the figure, we can give like what's the size and the heat map, and we define the data frame and the data frame correlation. So it captures the correlation between different variable, and a note true, what it does is it shows the numbers also, and then CMAP is actually different, the colors combination we want. So let me run this. Okay, so it's beautiful. So now you can see that how different variables are correlated to other variables. So the diagonally it's showing like, okay, it's the same, a correlation of the column with price, so price with price. But if we go other, so if we look at the second one, so it's saying 0.53, so that means area is correlated with price with 0.5. So as it goes darker, so that means it's highly correlated, and if it is lighter, then it's less correlated. So if you look the price and goes down, so it seems like the area is the highest correlated compared to other. And what we can do here is we can see the pair plot between the areas and the price as well. So let me run the pair plot. So now you can see here, as the area is growing, the price is also growing after rescaling it. So that means there is a pretty good linear relationship between these two. So now I think we can go ahead and use this variable as our model building. So let's start with splitting the data between X and Y. Okay, so what I'm doing here is Y train. So I use the data frame pop method to just pop the price, and then X train all the other columns. So now in the train set, I have used Y train. So as a nomenclature best practice, the Y is always the smaller case and X is the uppercase. So we follow this as the best practice. So please follow this as also when you're writing the code. So we will actually start with using the scikit-learn, with the stats model. So why specifically stat models, not the scikit-learn? So stat models actually gives a pretty good summary that you will see, and much better than the scikit-learn. But there is one caveat also with stat model is we need to explicitly add the constant, because in stat models the line goes through the origin. So uh, in order to basically make it move from the origin, we have to add the constant. So that's one of the caveat when we run the stats model. But yeah, that's basically, it's a small thing. So what we can use is, first let's import the stats model library and then store in SM as an abbreviation. So now we can use the add constant that I explained just now, and then we will start with the first our variable area. So here what we are doing is we are going through an approach that add variable one by one instead of uh, looking at all together. So we will follow different sort of approaches. So first we will go with adding one attribute at a time, and then add another attribute and see how the performance is improved, then add another attribute also. So we'll go slowly like that. So first we add the constant, and then so using add constant method, and then so now we will be using the stats model ordinary least square method for fitting the model. So let's run and fit this model here. Okay, so now let's look at the different parameters of this. So now the constant is 0.12 and the area coefficient is 0.046. Okay, so this doesn't give clear picture, but let's look at the summary. So this is the summary that I was talking about. So if I run this summary, so lr.summary, the stats model has a summary method. So if I run this, so it gives a clear summary of different metrics actually, and pretty easy to analyze. So first of all, R square, it's 0.28. So that means 28% of this model is able to explain the price prediction, and also adjusted R square. So adjusted R square is basically we panelize the model because sometimes we keep on adding uh, the variables, then the model will try to memorize the data. So in the multiple regression, so that's why we have it adjusted R square. And also, if we look at this constant and the area, so these are the coefficients. So there is a probability. So what this distribution is saying, if it is 0, that means the model coefficients are not by chance actually. So it is predicted by the model. It's not by chance. So in order for the model better and better model, we need to make sure this is always 0. So let's actually we improve the model by adding another variable. So what we can do is, if we go above in the pair plot, the heat map. So we see area, and then we can pick up that next as a bathroom. So it's also 0.52. So let's add that variable. So now let's add to our extrain LM and follow the same add constant and then ordinary least square, and then let's look at the parameter again. Okay, so now the parameter is, so if you will see 0.39 and then previously it was 0.46, so now it's little reduced because bathroom is also added. So what these coefficients are saying is the price will be increased by 39.39 unit if we increase the area by 1 unit, and similarly the bathroom will be increased, the price will be increased by 1 unit if we increase the bathroom by 0.29 unit. So that's what these coefficients are saying. So let's look at the summary now after adding one more variable. Okay, so now the R square is increased to 0.48, so 48% of the variance we can explain by this model by adding one more coefficient, and this seems 0, so that's pretty good, and the adjusted R square is also 0.47. So seems like adding a bathroom actually improved the model. So let's go ahead and add another variable. So if we go above, so now we can add bedroom as well. So 0.35, the correlation coefficient. So let's go, and it's already added here. So now let's do the same thing, add the constant in the stats model and then ordinary least square, and then let's look at the parameter again. Okay, so now the compare the parameters of 0.39, 0.25, and previously it was 0.39, 0.25. So the area is still the same, but bathroom is little bit reduced and the bedroom is 0.18. So that means again, like uh, the area will be, the price will be increased by 0.81% if the bedroom is increased by 1 unit. So that means area has the maximum impact on the price changes compared to the other attributes we have. Let's look at the summary now. Okay, so now the R square is moved to 0.50. That's a good amount of improvement. So 2% is also a good improvement, and the constant, the p-value is added as 0.022, so constant, but others are still same. So that is one of the approach. You go and add these variables one by one, and the other is actually you add all at one together and try to remove one by one where actually it's doesn't make sense, or basically it's not impacting, it's not affecting the price value. So now we will follow the second approach of adding all the variables together. So now what we can do here is let's look at all the columns. So looking at the columns is data frame.columns method. Okay, now we will follow the same add constant to all the columns and then ordinarily least square on y train and the x train, and then fit the fit. Okay, so let's look at all the parameters. So here, if we look at all the parameters, so area is reduced, but still area is the highest. So the negative coefficient value explain the price will be reduced by 0.03 if the unfurnished is increased by 1 unit. So it's in the opposite direction and compared to others. So basically others will increase, but unfurnished actually will reduce the price. So that's the way it's showing in the coefficient. Now let's look at the summary of this. Okay, so R square, that means it's 68% by adding all those. But if we look at the p-value, so we have lots of p-values. So that means if we see the p-values, basically it's point greater than 0.5, some 0.05, or some people say is like 0.5, 0.05, but it's basically if let's consider 0.05, so then it's also that means these variables are showing a multicollinearity, and these are redundant if you add them in the model, so we need to remove them. So 938 is a very big value, so that should be considered. But so also it clearly explains if the p-values is high, that means these variables are insignificant. So that means we need to drop these values. And also there is a better way also to look at like whether these variables are insignificant. That's called the VIF. So that's called variance inflation factor. So this helps actually to find out how much feature variables are correlated with each other. So it's a very extremely important parameter to test in our linear model, and it clearly explains, it quantifies basically that how feature variables are correlated to each other. And it's a we can use that using the stats model library. So that's the formula. So VIF1 minus R square. So let's use the stats model library and import the variance inflation factor. So what I'm doing here is I created a data frame and then I'm running the variance inflation factor on each of the extreme values and taking these values and passing it to this method. And what it is doing is it's calculating the values for each column and then storing that in the data frame. And then I'm showing that in the ascending order. So let's run this and see how it looks like. Okay, so now if you will look at the numbers, so what I explained is if the numbers are high, that means they are highly correlated to with each other. So in that case, bedroom has like usually the number more than 5 is actually considered that this should be dropped. So if anything is more than 5, we should drop off right away. So bedrooms is anyway showing 7.33, so that should be dropped. But as now we have two things, like whether look at VIF or look at the p-value, because p-values, if we go above, is very high in semi-furnished. So basically, if we want to first of all drop off, is we look for very high p-value and also look for VIF. So if the p-value is high and also the VIF is also high enough, then actually we take that one to drop first. So as the p-value is highest in semi-furnished and semi-furnished, the VIF is also 2.9, so we take the call of dropping the semi-furnished first, and then we will go through these numbers again. So let's drop the semi-furnished column and then using the drop and then column giving the 1. Okay, so now it is dropped. So now we will run the add constant again to the stats model. And let's see the summary again. Okay, so R square is still the same because as I explained, these are correlated to each other. That's why if you remove also doesn't impact much because other variables are already considered by the model. So p-values are also, now it's better actually. Now let's look at the VIF now. Okay, so VIF looks like bedroom is 6.59. So PIF is 6.59, and let's see the p-values, and p-values is also 0.206. So that means the bedroom can be the next variable to be dropped because it has a high py value and also high p-value and high VIF. So let's drop this one as it's not of much useful. So now let's drop the bedroom and then let's go through the stats model building again. And now let's look at the summary. Okay, so now still, as I explained, the R square is still the same. So now the bedroom is also dropped. So now it seems like the PIF value is in the decent shape. And let's look at the VIF. Okay, so now the VIF is also less than 5. So now the next high value is 0.03 in the p-value. So this is again becomes a candidate for dropping it, and also 1.87 it sends the VIF. So let's drop the basement and see whether there is a change in the model R square value. So we'll follow the same at the constant, run the auxiliary least square, and then look at the summary. Okay, so not much change in the R square after dropping that column also. And if we look at the p-values, now it seems in a very, very decent shape. So all this p-value looks good, and let's look at the VIF as well. Okay, that also all are under 5. So now this explain that that we starts with all the variables and slowly removing one variable at a time. And previously we add one variable at a time, and we were going towards adding variable one by one. So this is other way around approach. Now these two methods are actually a little tedious and takes a lot of time. If you will see, like we were going through adding one variable at a time, and then or we were removing one variable at a time. So this is a lot of time consuming, and the columns are less. But let's say if you have 50, 100 columns, you cannot follow this approach. So there is another interesting approach is called the RFA, recursive feature elimination. So this is a scikit-learn library that we can use to remove the features that are not important at once, and then once we reach to a decent number, let's say 10 or 15, then we can slowly remove one by one. But that is, we can easily eliminate these features, so we're using that method. So let's go through that and see how that works. So now we can import that using the scikit-learn feature selection, and this is the RFE class. And so let me run that, and also we imported the scikit-learn linear regression class as well. So why I'm saying class, because this is capital. So now how does this work is, let's say so first of all, I'm creating the instance of linear regression, and I'm fitting the model on X-train and Y-train, the linear regression model. And the RFE, so what I'm saying here is step 10 means like give me all the variables and maximum 10 that are non-correlated. So basically it's filtering all the variables until 10, and it rank each of the variable, and rest of the variable will be removed if they are not useful and they are not significant for the predicting the price. So, and then I pass the linear regression model and actually that how many variables I want, and then fit that RFE with X and Y train. So let's run this, and in order to look at the ranking and different columns, we have to unzip and then show that as a list. So let me run that. So now this is the ranking it's showing. So it's rank 1 is it's the most important factor, significant factor, and rank 2, and so basically it's rank 2, and then it removed rest of that. So let's see what all different columns actually. So we can store all the columns in the column variable. So using the RFE support method. So these are the columns that the RFE is saying are the significant for predicting the price. And the rest, these are the columns are removed that are non-significant. So unfurnished, semi-furnished. So some of them we already, when we were going through each variable at a time, we removed it. So now let's again go back to the stats model to look at the summary because stats model gives a pretty good summary. So let's use these columns as an extra in RFE, and then we go to the stats model and add the constant again, and then we run the ordinary least square method for, and then fit the model. And now let's look at the summary again here. So if we look at the summary, the R square is 60, so not bad. Previously, when we were adding one at a time, it was 68%. So, but you look at the power here. So all the p-values are also like almost zero. So that's, look at the power. Like we spend so much time in adding or removing the one, but here with just one command with RFE method, we were able to achieve 60% of R squared value, and also the p-values are also zero. So that's the power of R square. Now let's look at the VIF as well. Okay, and you can see like all the VIF are also less than 5. So that's what we were expecting also. So that's basically, so I recommend using the RFE also. And then once you remove all those columns, you can then try to remove each column one by one once you see like that if the R square value can be reduced or can be increased by removing few more columns. So now let's basically look at the residual analysis on the training data. So residual analysis is we subtract basically. First, we look at what model predicted, and we look at what was the original value, and we analyze that data. So basically, what we want to do is we need to check the error term. So that's called an error when we calculate the residual, and we need to make sure the error is normally distributed. So that's one of the major assumption for linear regression. So in order to visualize that, we can build an histogram. So first of all, let's predict the price. So we will use the model. So we will use that model that we initially created by removing variable one at a time. So LR4 model, and we will use the predict method to predict on the X train. So let's make the prediction, and we will use the C-bond dist plot to calculate the difference, Y train minus Y train price, and then let's see how it is distributed. So for the linear regression, it should be normally distributed and centered against zero. So you see it's linearly, it's normally distributed and centered at zero with a little bump here, but that's fine. It's very less, so we don't need to worry about it. So now we can go ahead and make the prediction for the test data that we created initially. So one important thing is the model is trained on the scale data, so we have to actually run the prediction also on the scale data. So we cannot just run on the data that we got initially. So we have to again scale the test data as well. So we already have these columns that initially we figured out like it should be scaled because we want to bring this between 0 and 1. So we are following the same for the test data also. So DF test, we got it from the test train split. And yeah, so one thing to note here is we are not calling the fit and transform because we don't need to fit this the test data, because the model in the training set, we want the model to look at the data and then calculate how much min-max scale or the normalization they have to do. But here we don't want then, because the model didn't saw the data. So basically, we just want them to transform it based on what they have learned in the model. So we don't fit it, we just transform it from the same scaling technique that they followed while training the data. So we just run the transform here this time. And once we run the transform, let's look at the test data again. Okay, so now it is spread between 0 and 1. So now let's divide the test data into Y test and the X test. Again, nomenclature, it should be lowercase and there should be uppercase. So we are running the stats model. So we will add the constant again the same way we did for the training data. So test data. So add the constant to this one. So now we will drop the columns that we didn't added it to the model because those were all correlated. So we have dropped those columns. So now let's make the predictions. We'll use the predict method and then we pass the test data. So we passed the test data and it predicted. So now let's evaluate the model. So we will plot the graph between the actual value and the predicted value. So what we are doing is we are using the scatter plot and scatter plot Y test and the predicted value. So this is the actual test value and the predicted value. And then this is the subtitle label we have added. So let's draw this as our last step. So now you see that these are pretty close, and then as the model has 68% R square value, so maybe some values are not matched, but a lot of values are pretty close here if you will see. So that's all about this actually. And then we have a couple of more options also. We can improve the model is by adding more features and build some non-linear model also. But with this, we are able to achieve to 68%, and by looking at the different. So if I scroll up here, so for the model, yeah, if I scroll up here, you can look at these numbers, and it explains that this is the area is the attribute is impacting the price the most, because the zero point 0.3 change in the price will be changed by 0.3 if we change the area by 1 unit. Similarly, the others are going. So that way we quantified also which variable is impacting the most, and we quantified these variable values also. And this is negative, shows like it goes in the opposite direction. So that's all about this housing price prediction project on using the uh, linear regression model. And so I hope now you got a good understanding of this project. So go through this video multiple times and please write this code by yourself. And I'll also put this code in my GitHub and then add this in the description box. So please go through this multiple times, and once you feel confident, then add this in your resume, so that it gives a good indication to the employers also that yeah, uh, you have worked on some good projects, and then this is a very good project to learn the multiple linear regression and try multiple times. And then if you have any questions, then please leave the questions in the comment section, and some concept you're not able to understand, then add the comment. I will go ahead and make the videos for those specific concepts. And if you like this video, then please subscribe to my channel, because that way I already told multiple times that gives me a signal that yeah, you want me to make such videos and you're interested in learning AI and AI and ML programming. So I'll keep making this video. So please subscribe to this channel, and thanks for watching this video.